Okay, hello again. We are going to do the next section, which is chapter 4.5, the last unit in chapter 4 we're going to cover. And this involves the graphs of tangent, cotangent, secant, and cosecant. So we did sine and cosine in the last one. We're going to expand what we've learned a little bit for these. And these are a little different, so we need to be cautious of how we approach them. Wait, what happened? What's going on here? Oh, because that's not one of that. Okay. No. There we go. Okay. So tangent is an interesting bird because it can be written as sine x over cosine x. And what did I always talk about we needed to be worried about in denominators? Yeah, that's right, zeros. And cosine can be 0 because cosine goes like this, 0, 0. This is one complete cycle for cosine, and it has 2 zeros in it. And that's in the denominator of the tangent function. So the tangent function is going to have some asymptotes, and we got to be careful about it. So when we graph tangent, let me try to do this neatly. So here's my x-axis. Here's my y-axis. Boop. Okay. And turn that off. Off. I got my pen. Yep. So I'm going to go ahead and draw sine first. I'm going to use green for sine, green for go. So it's going to go like that, and then like that. We're going to do another one. And we'll do one over here because what the heck, they're free. Okay, there we go. So it goes down up to 1, down to -1, and here is, oops, try to do it straight. There, there, and so these are the markers for pi, 2 pi, pi over 2, 3 pi over 2, blah, blah, blah. Okay, so this should be, so this is pi over 2, pi, 3 pi over 2, 2 pi, 5 pi over 2, 3 pi, and back this way, minus pi over 2, and it gets to 0 at minus pi. Okay, so there's our axis. And cosine starts up here, and it hits 0, and it goes down to a maximum, and it hits 0, and it goes up to its maximum, and it goes down to 0, and it hits another maximum. And on this side, it goes down to there, hits 0 here, and then it goes down to its maximum there. Okay, so where we have can I make this a dotted line? Oh, that'd be awesome. What does that do? I don't know what that does. Go away. Okay, so I can't make a dotted line. That's too bad. Okay, so we're going to have an asymptote wherever cosine is equal to 0. So at all of these places, there's going to be a big fat asymptote. So I'm going to put one here, and one here, and one here. And cosine goes to 0 here, right? Blue is cosine. So this is cosine x, and the other one is, this is sine x, okay? So when we look at, I really like that heavy marker thing. Let's do that, and let's do that in people. There we go. Okay, so sine over cosine. Here, sine is positive and cosine is positive. So tangent's going to be positive over positive. It's going to be positive here, but it's going to be negative here. Okay? And when cosine gets close to 0, like right here, you're going to have a negative number divided by a really small number. So this is going to give us a really big negative number. We're going to approach negative infinity down here. And when we pass through here where sine is 0, then the whole function is 0. And then this shoots back up to infinity. So I think of it as, in this first phase right here, right around the origin, I think of it as tangent following sine. And the asymptotes come from the denominator, from cosine. So cosine, when it's at 0, the function blows up to infinity. But then it's going to repeat itself. Notice here, cosine is really small and negative, and sine is positive. Well, if you have a small denominator, you're going to get a big number, but it's negative down here. So we're going to get another negative. And over here at this asymptote, both sine and cosine are negative, so it's going to be positive, but we're approaching the asymptote, so we're going to shoot up to infinity. And likewise, this one's going to do the same. And over here, if we had another asymptote, it would be the same thing. So that purple graph is the tangent. You can confirm this by graphing tangent on Symbol Lab, and you'll see the same thing. You can look up graph of tangent x online, and you'll find the same thing as well. Important things to notice is, notice the period. How often does it repeat itself? Well, let's see, it goes from here to here, and then it repeats here to there, and then it repeats here to there. The distance from here to here, let me figure it out. 3 pi over 2 minus 1 pi over 2 is 2 pi over 2. So the period, of tangent x is pi instead of 2 pi. It's half what sine or cosine is. The period of tangent x is pi. Do you think that's important to note somewhere? I don't know. Sometimes you can tell by the way the professor writes on the board if something's important or not. I don't know. You decide. Okay? Now, the asymptotes occur where cosine is equal to 0. You can see here's where cosine equals 0 right here. That's where the asymptote is. Tangent is 0 when the numerator is 0, when sine is 0. Something you should probably note. This is the graph of tangent x. Okay? Now, let's look at y equals cotangent x, which would be cosine x over sine x. So let me make my little thing again. I'll use Poiple. Okay, and I'll draw sine first because that's always easier. Whoa, that's not it. Turn that off. Sine, 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 and I'll give one more here, sine. Okay, and then I'll do cosine. I gotta mark these spots, otherwise it's really hard to draw cosine. And we got those two. We got here 2 pi. And this is 2 pi plus a half, so that'd be 5 pi over 2. And here's 3 pi, and we got minus pi over 2 and minus pi. So this is minus pi. minus pi over 2, 0, pi over 2, pi, 3 pi over 2, 2 pi, 5 pi over 2, and 3 pi. Okay. Oh, and so I got to draw cosine. So cosine will go like this. So I'm going to draw it like this. It's going to go from here. Whoops. Going from there to there. So it's going to go to there, to there. Oops. Always got to do these carefully because it's really easy to screw up cosine. Okay. Now this time, the asymptotes are going to occur when the denominator is equal to 0. So that's when sine is equal to 0. So there's going to be an asymptote there, and there, and there, and there, and there. So here's our asymptotes. When the denominator is equal to 0. And over here. Okay, those are our asymptotes. Now we got to think about how this works. And let's get my pen. Let's do it in green, but a dark green. There we go. Okay, so we got to figure out where is it at infinity or negative infinity. So right in here, the function is, the denominator is close to 0, so that's going to make it blow up to infinity, but both of these are positive. So that tells me that it's going to be up here at positive infinity, and it's going to come down to 0, and then it's going to shoot back down to negative infinity, because notice sine is positive, but cosine is negative, so negative over positive gives us a negative. And it's going to repeat this pattern. Okay, so cotangent and tangent look a lot alike, except the zeros are where sine is equal to 0. That's, I'm sorry, the asymptotes are where sine is equal to 0. And it's 0 when the numerator is 0, when cosine is 0. So the whole thing looks like it's shifted by pi over 2, I think. And the period of this thing, whoops, period of cotangent x is pi, just like the other one, because this distance from here to here, that distance is pi radians. So it repeats itself every pi radians, that's its period. So of course, if you had something 2 cotangent 3x, the 2 stretches it vertically, but you really can't tell because they're going up the asymptotes. But the 3x would make the period, instead of being 2 pi over b, it'd be pi over b. So you'd get pi over 3. You'd fit 3 of these curves within pi, so it would be pi over 3 is the period of it. I'd be really surprised if we're going to do anything like that. We might, but probably not. So this is cotangent, okay? Now, let's get cosecant x, and that's going to be 1 over sine. So let's draw sine, shall we? We shall. There. And there. And oh, turn off. Turn off. There we go. So sine is going to be like that, and like that. And there's another little humpity hump over here. And I'm not really worried about the markers in between here because I'm not drawing cosine. But I notice that it's possible to get a 0 down here. In fact, look, there's a 0 there, and a 0 there, and a 0 there, and a 0 there, and a 0 there. So there's all kinds of asymptotes all over the place. It's going to have an asymptote anytime sine is equal to 0. And you need to be able to recognize that when you see these things and explain that. I may ask you to do an interpretive dance describing cosecant, and you need to motion that. I'm kidding, you're not doing an interpretive dance. Okay, so sine at its highest point is equal to 1. So what's cosecant going to be? 1 over 1 is 1. It's going to be right there. Cosecant's going to start right here. But as the sine gets smaller, 1 over a small number tends to be a big number. So as this gets smaller, cosecant gets bigger and bigger and bigger, and it takes off like this. When sine is negative, cosecant is negative. So it has these asymptotes where sine is equal to 0. It starts at 1, and it's either bigger than 1, right? It starts at 1 and goes up, or it starts at -1 and goes down. You will never see cosecant, x equal to 0.5. Because at 0.5 here, if this is 1, the cosecant graph doesn't even exist. If you try to calculate this, let's see, if I'm going to solve for this, I would write this as 1 over sine x equals 0.5. And maybe I'll cross multiply so I get sine x, 0.5 sine x equals 1, divide by 0.5, sine x equals 1 over 0.5, which equals 2. Try to do inverse sine of 2 on your calculator, and you're going to get an error because 2 is up here, and the sine function only exists between 0 and 1. And so you can't solve this. There's no solution because we originally started with cosecant being less than 1, and between 1 and -1, this is no man's land for cosecant. It doesn't exist here. It has no meaning. So if you have to solve for cosecant x equals 0.5, well, you're not going to get an answer because it can't happen. You're going to get an error. Okay, so the blue is the graph of cosecant. That was fun. I know it was. Yeah, thank you for saying that. That was nice. Okay, now, we're going to turn that off, secant x, which is 1 over cosine. How do you think it's going to compare to the last one? Yeah, really similar. You're exactly right. Except we got to draw cosine. I hate drawing cosine. Okay, so as I've learned, turn that off. Instead of starting here and trying to draw cosine, I start over here. Maybe we'll stop there. And maybe we'll give it another little hump. Oh, well, we kind of made it. How can I stretch this? No, I can't. It doesn't help. Okay, but whatever. You get the idea. So here, when cosine is 0, right here, and here, and here, and here, and if I go off the monitor, there'd be 1 over there. This is where the asymptotes are going to be, when the denominator can be equal to 0. And again, you need to be able to identify that. Whenever we look for asymptotes, we look for what happens when the denominator is 0. And now, let's think about what cosecant will be like. Cosecant is going to be, well, and cosine is 1, cosecant is 1. So it's just like with secant. It's going to touch the cosine curve right there, but it's going to go up like this and like that. And here it's going to be like that. Does it really matter if you draw the arrowheads on the ends of these? Yeah, probably not. I do it because it looks pretty, but you don't have to. I would not mark you wrong if you didn't put the arrowheads. Okay, so the red curve is cosecant. Notice we're still going from here, this is minus pi over 2, to here, which is, so that's 0, pi over 2, pi. What am I doing? I want to go from here to here. So this will be 3 pi over 2. So if I want to know the period, I need to know what that distance is. So it's 3 pi over 2 plus 1 more pi over 2, which equals 4 pi over 2, which equals 2 pi. So the period of secant and the period of cosecant are the same as their respective trig functions, cosine and sine. So this has a period of 2 pi. If you have y equals 5 secant x, well, then instead of this going up to 1, it goes up to 5, and it goes down to negative 5, because that's what cosine would do. Cosine would go from plus 5 to negative 5, okay? Because this would be y equals 5 times 1 over cosine x, right? Anyways, so it would go up to 5 and negative 5. That doesn't make any sense. But anyways, so this is secant. So we got secant, cosecant, tangent, cotangent, sine, and cosine graphs. Man, this is fun. So anything else on here? Okay, so now there are some homework problems that will say secant x equals 1.5. Solve for x. How do we do that? We don't have an inverse secant, but you can write this as 1 over cosine x equals 1.5. Cross multiply 1.5 cosine. You understand what I cross multiply? Multiply those two together and multiply those together. Divide by 1.5. 1 over 1.5 is, what is that, 2/3, 0.67. So now I can do cosine x equals 0.67. So I can do inverse cosine of 0.67, and I'll get the angle. And that's the solution to this. Now I want you to notice another way to solve this. If I have 1 over cosine x equals 1.5 over 1, I can take the reciprocal of both sides and make this cosine x equals 1 over 1.5, because I'm raising both to the -1 power. The times when you cannot do that is 1 over x plus 2 equals 1/3. You can't take the reciprocal and say this is x plus 1/2 equals 3. No, 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 no. You would have to do it like this, and that would become this would become 1 over x plus 2. You just made it really hard. Okay, you cannot distribute an exponent across a sum. I'm going to harp on this because I see students up way past calculus who still screw this up. So you can't distribute that. You can take the reciprocal of both sides if there's one thing on here and one thing on that side. Then you can. And even if it's 2 over cosine x equals 1.5, you could say cosine x over 2 equals 1.5. That flipping both sides lets you get cosine into the numerator, which is a great way to do this. If you're unsure, cross multiply. If you have 2x plus 3 equals 5/4, you're not going to cross multiply. But if you do cross multiply, you would get 4 times 2x plus 3 equals 5 times 1, right? Probably not going to cross multiply there, only if you have x in the denominator. Okay, so take a look at the homework. You're going to have questions. Come get help early. If it's 11:30 at night and you're just looking at this stuff and you're just starting the homework, then you're going to have troubles with this, and you don't get any sympathy from me. So please come to the homework session, come to the office hours, get help, and I will be happy to help you, okay? And that's it for chapter 4. Bye.